Now we're looking at decision trees related to decision theory. We use decision trees to calculate the expected payoffs for different decisions. As usual, I believe the best way to learn something is by demonstrating it, so we're going to look at an example. I won't say it's a brief example, but it's certainly a very thorough example. So we consider a business. The business needs to make a decision regarding the purchase of stock. The stock has a 55% chance of increasing. If the stock goes up, the business makes a profit of 15. If the stock goes down, the business obviously makes a loss of 12. However, we have another choice. The business could pay a financial advisor some amount of money, X, for assistance. The advisor is 70% successful at predicting stock increase, and he's 60% successful at predicting stock decrease. So you look at all of this and you think, how am I going to get this into a decision tree? Well, I'm going to do it for you to the best of my ability. So we draw a decision tree, and we use what I call a four-part process. So, process 1. Set out the possible decisions and outcomes. For this, in terms of notation to do with the decision tree, it's important to note that decisions are square boxes and variable outcomes are circular. So now let's draw our decision tree. So we have a first decision. We can choose to buy the stock. We can choose not to buy the stock, and we can also choose to ask for the help of an advisor. Now, if we buy the stock has a variable outcome that it can go up or down. If we don't buy the stock still may go up or down. Now, if we make the decision to ask for the advisor, we still obviously have the variable outcome that he tells us to buy or tells us not to buy. Now, these give us decisions. Now we can choose, having our informed input, whether we buy or don't buy. And if he says not to buy, we can choose whether to buy and not to buy. So say that he tells us to buy, there's a chance, variable outcome, that it may go up or down. Similarly, up or down. So there we have the outline of our decision tree. I'm going to quickly add some details to it. So now that we've drawn out and labelled our decision tree, we move on to part 2 of the 4-part process. And part 2 is to calculate the return for every combination. So we move back to our decision tree. So if we buy and the stock goes up, as you remember, we make a profit of 15. And if we buy and the stock goes down, we make a loss of 12. If we don't buy, we have 0 either way. Now, when it comes to taking the financial advice and we're told to buy or not to buy, we've immediately paid X amount of money for the gentleman's help, or the gentle lady. So we have stock up 15 minus X that it costs for the financial advice, and similarly for every decision that follows. If we don't buy, we still have to pay for his advice, and the same follows down here. No matter what advice he tells us, we're still paying him X amount of money. So what we've done now is we've calculated the return for every combination, and that should, in theory, tick off part 2. So part 3 is to find the probability of each outcome. So how do we do that? In this case, it's a bit of a lengthy process, so we're going to speed it up as much as we possibly can. So the trick here is to go from the left to the right. So we're going to let U equal stock up, D stock down. Y is if we're told yes by it, and n obviously is if we're told no, do not buy. So going on what we have already, we know the probability that the stock will go up, and therefore of course we know the probability that the stock will go down, which is 1 minus this. And similarly we know the probability yes given up. So the probability that the financial advisor will say yes given that it has gone up is 0.7, and the probability that he'll say no given it's gone down is 0.6. Now crucially, we also know the opposite of these values. The probability that he will say no given that it's gone up is of course 0.3, and the probability that he'll say yes given that it's gone down will be 0.4. So bear that in mind if you're calculating your probabilities for your decision tree. I'm not going to go into too great a detail because this is all sort of due to your choice. So we need to know probability yes, probability no, probability up given yes, and the probability to go down given yes. So quickly we know that Py is equal to probability of y given u multiplied by probability of u and probability of y given d Pd, and if we just plug in the values we have 0.7, 0.55 plus 0.3, which is 1 minus what we spoke about just a bit earlier, times by 0.45, which gives us 0.52. Now of course if we have the probability of yes being 0.52, then the probability of no is 0.48. And we use Bayes' theorem to calculate probability of down given yes, and of course probability of up given no, and they follow quite simply. And if we plug in all the numbers, we should get 0.35. And therefore we know the probability of up given yes, which is 1 minus 0.35, which is 0.65. And by the same method of Bayes' theorem, we can find the probability of up given no, if we skip the calculation, is equal to 0.34, and by the same method, probability of down given no is 0.66. So how do we apply all of these values and probabilities to our decision tree? So now we have a decision tree. We know the probability going up is 0.55 and probability going down is 0.45. Similarly for here and of course here. So let me just move this up here. Now that we've calculated all of our probabilities, we know now the probability that he'll say yes is 0.52, and the probability that he'll say no is of course 0.48. So the reason that we calculated all of these is so that we can use them all on this part of the table mainly. So the probability that it will go up, given that he said yes, we've calculated that, and we know that's 0.65. And the probability that it will go down, given that he said yes, is 0.35. And the same goes here, and here. Okay, so how about the probability that it will go up, given that he said no? Well, that's equal to 0.34, and hence we have 0.66 here. Well, the good news is now we're on to the final part of the process, part 4. And in part 4, we use the conditional probabilities to calculate the expected return at every option node. So we work from the right to the left on our decision tree. We choose the decision that maximizes the expected return at every decision node. So I'll quickly write this down. We use the conditional probabilities to calculate the expected return at every option node. So we work from the right to the left. So how does this affect our decision tree? Well, if we take 0.55 and 15 and multiply them, and 0.45 and minus 12, multiply them, and we have 0.55, 15 minus 12 lots of 0.45, and we have 2.85 as a value up by here. And the same follows that we have a 0 here. Now what do we do when it comes to the slightly more complicated expected values here? Well, so take for example 15 minus x minus 12 minus x with probabilities of 0.65 and 0.35. We have 0.65 times by 15 minus x plus 0.35, lots of minus 12 minus x, and that's equal to, after a bit of calculation, 5.55 minus x. So what you do here is you write that on the decision node, the variable outcome node, sorry, which goes here, and we repeat the process for here, here, and down here as well, multiplying minus x 0.65, minus x 0.35, and we write down all the values, just like this. So here we're left with minus x. At this point we have minus 2.82 minus x, and another minus x down here. So, as I said in part 4, we choose the decision that maximizes the expected return at each decision node. So the decision nodes down here, we have to choose the maximum, and the maximum of course is 5.55 minus x, because that's bigger than minus x, because we actually have a value here. So and at this decision node we have minus 2.82 minus x and minus x. Of course minus x is the largest. So now we're left with a bit of a conundrum here. Obviously 5.55 minus x is larger than minus x. So at this decision node, we obviously don't choose 0, so do we choose 2.85 or 5.55 minus x? Well, if we equate the two, we can come to a conclusion. (2.85) equal to 5.55 minus x, we have a value of x equals 2.7. So what does that tell us? It tells us we accept the advisor if he's charging less than 2.7. Otherwise, we make the decision to buy stock. Thank you for watching.